Hello everyone. Assalamu alaikum. The title of our thesis is Atomistic Modeling of Functionally Gradient Wettability Surface and its implication on thin film liquid vapor phase change phenomena. We were supervised by Dr. Mohammad Nasim Hassan sir. I am Mahmudul Islam and I am going to present today along with Shariar Alam and Mohammad Shahjadullah Thakur. So this is the outline of our presentation. We have motivation, introduction, objectives, simulation domain, methodology, results and discussion, conclusion, and finally recommendation. After the characterization of boiling curve in 1930, phase change heat transfer has garnered much attention from both academics and industrialists. There are a number of potential applications of phase change heat transfer on nuclear power plants and electronic cooling. Phase change heat transfer depends on liquid film thickness, heating rate, surface geometry, and most importantly, surface wettability. Surface wettability is the ability of liquid to keep contact with solid surface. It depends on the intermolecular interaction between liquid and solid surface. We use contact angle to quantify the degree of wettability. As we can see from this figure, as the value of theta is less than 0, the surface is hydrophilic. And when the value of theta is greater than 90 degrees, the surface is hydrophobic. And besides them, there are a number of special wettability surfaces. One of them is wettability gradient. In wettability gradient surface, one part of the surface is hydrophilic, other part of the surface is hydrophobic, and the wettability gradually varies along the surface. And when this gradual variation of the wettability depends on a particular function, we call it functionally gradient wettability surface or FGW surface. Now, there have been a number of contemporary research on different types of special wettability surface. We have dotted pattern surface, philic phobic surface, square array wettability, biphilic wettability. But no study has been conducted on FGW surface. So our objective, we aim to develop a method of modeling FGW surface. Then we're going to carry out atomistic simulation of thin film phase change over FGW surface. We're going to compare our heat transfer characteristics from classical thermodynamics and rule of mixture to find any additional heat transfer mode. And finally, we're going to understand and explain the enhancement due to convective effect. Now, this is our simulation domain. And our simulation domain is a three-phase system. There is a platinum surface at the bottom of the domain. Above it, there is liquid argon, and the rest of the simulation domain is occupied by vapor argon. We have used two different gradient functions, which is power law and sigmoid function. In our boundary condition, as we can see, x and z direction are periodic, and y direction has been kept free. Now, we have done molecular dynamics simulation with Lennard-Jones potential function as atomistic interaction function with time step 1 picosecond. On the right side, we can see that this is the potential function, and there are two important parameters, epsilon and sigma. Epsilon is called potential well, and according to Hens et al., potential well epsilon, as we increase the value of epsilon, the surface becomes hydrophilic, and as we decrease the value of epsilon, the surface becomes hydrophobic. And in order to conduct our simulation, we first have to model this surface. In order to model our surface, we first create a hydrophilic surface. And then we replace the hydrophilic atoms with hydrophobic atoms according to the gradient function discussed as we discussed previously. As we can see, the value of epsilon and wettability gradually changes along the z-axis with different values of p. So with our present modeling scheme, we have developed 10 different surfaces. And these surfaces are as we can see, these are the surfaces. And we have conducted thin film phase change heat transfer above these surfaces. Now, Shahriar will continue this presentation. Thank you.
Thank you, Mahmudul. Now I will continue with simulation procedure. First of all items were equilibrated at 90 Kelvin temperature for 2 nanoseconds. For 0 to 1 nanosecond, we kept the Langevin thermostat on, and for 1 nanosecond to 2 nanoseconds, we kept the Langevin thermostat off. We calculate our atom propagation using velocity Verlet algorithm, and after 2 nanoseconds, Langevin thermostat was turned on to raise the temperature to 130 Kelvin, and all was done using NVS ensemble and lamps. For the validation of equilibrium characteristic, we use argon, and we see that the density of argon is found close with the experimental value. System energy was also fixed after a time, and the total energy was found from the kinetic energy and the potential energy. From the temperature, we see that the temperature was fluctuating around 90 Kelvin, and the pressure was fluctuating around 0.07 megapascal to 0.25 megapascal, which is the saturated pressure of argon of argon. Now, from the phase change characteristic, we see that the hydrophilic surface encourage the rapid evaporation, and on a hydrophobic surface, it occurs slowly. But if we increase the value of P, it encourages the evaporation, and we find that we have non-uniform thickness due to the non-uniform evaporation. And for the evaporation number, we defined a cutoff distance 0.54 nanometer, in which we define that if we find less than 7 atoms around it, we call it vapor, otherwise it's liquid. And the net evaporation number was found from the difference of total evaporation number and the initial evaporation number. And as the value of P is high, the net evaporation number gets high. And from the argon pressure, we see that as the P value is high, we get high pressure, and at equilibrium, pressure depends on the potential function, which is directly proportional to P. And for the heating period, we got higher pressure but at a high value of P, because high value of P results in high evaporation number in constant volume, which results in high pressure. For the argon temperature, we see that the hydrophilic surface works more, and it creates a continuous way for heat conduction, and the heat transfer becomes smooth, so the temperature is high. And as the heat transfer is smooth, we get also high heat flux. So higher value of P indicates that high heat flux. And now we here shows the comparison between molecular dynamics heat flux from MD and thermodynamics. We found a close value from which we can say that we can use this macroscopic approach to the nanoscale within order of magnitude. And all these calculations were done using these equations. And finally, we find the molecular dynamics heat flux and the heat flux from the rule of mixture, and we compare them. We find a deviation. This deviation indicates that there occurs another mode of heat transfer. We call it local convection heat transfer, and this occurs due to the temperature gradients on the substrate. Now, I'd like to ask Mohammad Sajidul to continue.
Thank you, Shahriar. Oh, I'm muted. Sorry. Oh. Thank you, Shahriar. We studied sigmoid gradient wettability surfaces because of a special characteristic of the sigmoid function that ensures equal proportions of hydrophilic and hydrophobic atoms throughout the entire surface, regardless of the value of S, as we can see here. And yet, the phase transition is the same as PFGW surface in the sense that it is initially not significant, most rapid for the hydrophilic, and slowest for the hydrophobic. However, the thickness of the argon film here does not vary with the value of S, the function parameter. This is because the function parameter does not vary the proportion of the hydrophilic and hydrophobic atoms on the surface. And yet we do see some uneven distribution of the argon atoms over the SFGW surface.
Remaining.
And if we look at the net evaporation number and the argon pressure, we see that for lower gradients, and S equal to 1, there is higher net evaporation number and higher argon pressure. And the similar trend is seen for argon temperature and also wall heat flux. If we look at the average wall heat flux and compare it with the rule of mixture prediction, we see that the pattern surface gives higher heat flux than the rule of mixture prediction, and the SFGW surface gives even higher than the pattern surfaces. And we can see that for the smallest gradient of S equal to 1, we get the highest heat flux, and as the gradient increases for S equal to 10 or 5, we get higher, we get lower heat flux. To explain this, we look at the temperature contour of over the surface, and we see that for the hydrophilic, the surface heats uniformly, and so for hydrophobic. However, for S equal to 1 or S equal surfaces, we see some temperature gradients on the surface. If we take a closer look at the contour, we will see there are some local spots of hot and cold next to each other, which is due to the hydrophobic and hydrophilic atoms being next to each other in the surface of SFGW. Therefore, to conclude, we can say that PFGW surface gives higher evaporation rate and heat flux as the value of P increases. Classical thermodynamics can be applied within certain limitations. Average heat flux over FGW surface is always greater than the rule of mixture prediction, which indicates some additional mode of heat transfer. And SFGW surfaces having identical weighting proportions, and yet they give better heat transfer than the patterned philic-phobic surfaces that are traditionally used. And by studying the temperature profile, we understood that this enhancement is due to the local convection regimes that are generated by the gradient of the surface. And therefore, we recommend that using periodic SFGW surfaces, instead of philic-phobic periodic surfaces, will give better heat transfer. And future research works may investigate the effect of using other functions, using calculating the other material properties such as thermal conductivity and specific capacity on FGW surfaces. They can also investigate explosive boiling or Leidenfrost phenomena, or thin film boiling of refrigerants such as water or R134A, etc. And since we have also built a NanoHub tool in addition to our thesis, people can use this NanoHub tool to study atomistic modeling and research on functionally graded materials using the same principle of functionally graded wettability surfaces. Thank you.